There is an evolution from federated systems through AMA to advanced avionics, and these has been also driven to increase capabilities, reduce weight and cost and power consumption. And also, there's also an increase on the functionality and therefore computing performance that can only be realized by the use of multicore processors. The other dimension is that avionics domain is a tiny market compared to the mobile phones gaming industry. Therefore, having specialized processors for specifically addressing the safety critical requirements is a challenge. There are some solutions that custom-made processors, but the default one is that avionics industry has to use the processors that have been available and developed by chip manufacturers. Single core processors are still a preferred solution if you can, much more simple, CAST-32A doesn't apply, but there is the risk of obsolescence. So there is all these pushes the industry to upgrade to the path of providing or using multi-core processors. Multi-core processors are complex beasts. I remember the time when we started looking at the first single core processors, timing analysis on a 6820 or 750, block diagrams, they are not even at scale. If we put the scale from probably 750 compared to NXP, it will sit probably on the space where you have the little T here on the first cluster on the 2080. So the exponential growth of complexity means that they are very difficult to understand. And not even, I will say, even chip manufacturers have a full understanding at the cycle level how processes work. And that has driven certification authorities to provide additional objectives to perform the verification. Now, the key focus we try to understand here, and this is the whole concept, is the issue of interference and the impact that it has. Interference, as the CAST-32A definition, is a property that can cause, an interference channel is a property that can cause interference between applications. And this interference is extra delay, which in cases where by running two applications on two different cores, they are barely affected. Others may be affected by a factor of 5, 10, 20. The question is, the impact can be very, very high. Therefore, there has to be some level of quantification. The traditional notion of shared resource and interference channels is the use of memory, buses, caches, and when they are shared, that resource is slows down in a direct way, just because it's not available, but also by side effects, for example, changing internal state and then the reprogramming of that state also causes delays. So as part of the CAST-32A, the effort of CAST-32A is on providing a series of objectives to complement the DO-178C, which we understand that was designed, conceived before the time of multicore processors. And there are two of the objectives that we're going to be talking in particular here. There's a few more I'm going to explain later. But the key one is MCP-1, which is basically saying you have to do worst-case execution type analysis to guarantee that all applications will finish within allocated time. The means to do that is understanding what are the shared resources. And there's a specific objective on CAST-32A called MCP Resource Usage 4, which requires you to identify the resources, how it is allocated, and verify what are the demands on those resources. So what is the load on the bus? What is the impact of interference on contention of the cache, but also we want to extend that to other what I call hidden interference channels. The impact, for example, that a processor when it overheats because it's doing too much floating point calculations may have a side effect of lowering the clock frequency and therefore delaying the whole interference. In that case, a floating point unit could be called as a shared resource because it has a potential interference channel. Please know that in all the concepts described here today, the notion of worst-case scenarios and worst-case behaviors and guarantees is implicit. So this webinar is not an overview on CAST-32A, but it's important to put as a context what are the objectives, what are the implications. So there are two objectives related to planning that the applicant will put as part of their PSAC or the PHAC. There are objectives related to resource usage that are part of configuration settings and how to demonstrate that an accidental alteration of this configuration settings as has been properly mitigated. The key ones are the issues on the identification of resource usage, which is interference channel analysis, and its quantification. There's two aspects here that is important to reflect. Is one aspect of the analysis is what we call hardware characterization, the understanding of what are the actual impact of the potential share of a resource. Let's say, for example, that the resource that you want to identify is access to the coordinate fabric on a T2080. Understanding where the execution time or the transit on an empty bus or bus that is only used for one core is in relation to when there's maximum traffic. This is one of the activities we do in as part of research usage 4 and what we call hardware characterization. And this can tell you which are the resources who have a potentially negligible interference, and therefore they can be not ignored, but accepted that they don't need to be mitigated, and which are the resources that have a potentially huge impact on the interference, and this one needs to be mitigated or avoided. There are two additional objectives, more related to the application, which are software 1 and software 2. So one is worst case execution time analysis, which now means that you need to identify, with the understanding of the hardware characterization, how long your application takes to run in the worst case, and the isolation, but more importantly, in the intended final configuration. And we have a methodology to facilitate that analysis by running the application together with the maximal set of interference that it can suffer by running specific interference generators that we call rapid immense, and that provides an upper bound of that application. NCP Solver 2 is a repetition of the data coupling coupling analysis, which is very important when you have an integrated system, and is not really related to timing analysis. And there are some other ones related to error handling, and finally producing the final results. Key part here to understand is that not all these objectives apply to the same level of criticality. So DAL A and B are the yellow boxes. If your system is DAL C, you only have to do the white boxes. Know that the detailed hardware interference analysis of resource usage only applies to DAL A and B. However, worst case execution time analysis that does require a level of understanding of the resources does require some level of resource analysis. So worst case execution time analysis does need, even for DAL C, a level of understanding of the resources and interference. Perhaps the only difference is the rigor and the analysis detail that is required to satisfy usage 3 and usage 4. So going to this in a bit more detail, we achieve the objective of multi-core NCP Solver 1. It is required to understand what is the worst case execution time of all hosted solver components. First, understand that they work correctly and they have sufficient time to complete within the allocated budget. Now, there are two approaches or two options as specified in CAST-32A, which has caused me tremendous amount of headache to try to explain, because the terms are well defined but understood in different ways. Now, there is a term that is used that refers to robust partitioning. This basically means that if there is a mechanism that guarantees that a resource is not going to be used, an application is not going to use more than allocated resources, then it is possible to do analysis in isolation. You don't have that robust partitioning mechanism, whatever that is, then an additional or alternative way of performing timing analysis needs to be performed, which you either need to provide an interference mitigation or avoidance. And in any case, best practice is that you need to provide a level of timing analysis on the final full intended configuration. In any case, the analysis before, or the worst case execution analysis requires a different levels of granularity and results and iteration process. That's what we're going to do today. So even if you have robust partitioning, you still have to do some work to demonstrate that partitioning is effective. If you don't have partitioning, you also have to do the same amount of work to perform the analysis itself. So my interpretation is these at this point, and these are the only changes that focus on where the amount of work needs to be performed. The second part of the dimension is the specific identification of what are the resources, shared resources, and the potential interconnection based on the configuration, the critical configuration settings, and with the understanding of what are these resources and what is the potential impact, then we can perform a set of analysis that we propose to do through experimentation, carefully designed experiments, to verify that these resources don't achieve, are not being used beyond their budget levels. So this seminar today is not, or webinar is not to talk about CAST-32A, it's more the practical use of what are the tools, features, and capabilities that the RTOS provides to do partitioning, and then the means of verifying that that partition is effective, so that we provide evidence to support these objectives. And I would like to pass the token to Olivier, which described how those mitigation of interference through partitioning can be realized with VxWorks. Olivier.
Thank you, Guillaume. So, a few words about Wind River. So since almost 40 years now, we are providing mission critical and safety critical systems, software-based, that some of them are used in aircraft which are already flying. So this is a field we know very well. And for some of you that already know Wind River and know in particular that we were part of Intel, since 1 year we are no longer part of Intel. Just a refresh if you miss that information. So how the solution, in particular the RTOS, can help. So let's start by one point that was highlighted by Guillaume, which is the software one objective of CAST-32A. So here it's about having sufficient time to complete execution. So how you control this. And the two use cases that Guillaume described is one is the platform with robust partitioning, and the other one are all the others, pretty much. So I'm going to elaborate a little bit more, and maybe Guillaume will give you some ideas on the robust partitioning one, exactly what does that mean or what can help, hopefully. And we are going to look at, for each of them, how the RTOS can help. So one of the candidates, in particular for case one, is the OS, is usually the candidate to help on robust partitioning to make sure that this is enforced. And so you can claim that your Multicore platform is part of the case one. Then on case two, pretty much that's a subset of the first one, that you still want to mitigate interferences. And you can use several means that we would use for the robust partitioning to mitigate interferences. So let's go in further detail. And let's start by the very start point. Is what we want to achieve here. It's pretty much to control the Multicore resources. So here I'm using another example of Multicore than the one that Guillaume used, and just to show that pretty much the issue are the same. You need to identify the piece of the hardware you're going to use, see how you will use it. So it's not only identifying them, but seeing how you will use them, and see how they need to be integrated. So meaning which one are shared. So obviously the memory, the cache, and the interconnect are the candidate that will be always shared. But then you need to also look at the IOs, the conventional peripheral that you use, a PCI Express, or I would say some other buses you want to use. So you need to identify all of them and see how we want to mitigate. And depending on the different Multicore, I would say what you will have to do will be different. So that's why the start point needs to start the analysis of the hardware. So the solution I'm going to talk about, because when we talk about the partitioning aspect and the feature available, we have several safety solutions. The one I'm going to talk about is the one that applies virtualization. And amazingly enough, we are providing some solution that use an hypervisor and multiple guest OS for more than 15 years. They say, how can we do that? In fact, even in the single core world, a lot of people, in particular the one doing integrated modular avionics, wanted to do robust partitioning to allow mixed criticality and incremental certification. So we already use, even on single core, an hypervisor kind of approach. So the hardware was not helping much at that time. With the new multicore generation, then the multicore provide more means like the hypervisor execution layer, which is very useful to allow more capabilities. But that's the solution I'm going to talk about. Most of the things I'm going to discuss and present here would apply also for what we call the native solution, where you have a single OS that controls all the multicore aspects. But I thought that it was more interesting to talk about this hypervisor one because it has more capabilities. But bear in mind that a lot of what I will talk about could apply also with the single OS solution. So let's look at case one and what needs to be done. So when you want to define a robust partitioning multicore platform, still you need to comply with CAST-32A, that's obviously. But the key point that is described there is you need to provide robust resource and time partitioning. So the good thing in CAST-32A is really talk about robust resource partitioning, because most of the time everyone talks about time and space partitioning. Time and space partitioning is just one aspect of the equation. Resource partitioning is really one of the key points. So who are the candidates, who are the projects that may want to go into that case one? Pretty much they are the same one that we're doing robust partitioning or even on single core, which is you want to do integrated modular avionics. What does that mean? That means that you may want to put together multiple applications that comes from different suppliers that are independent from each other. So it's easier from a product management and integration management point of view to do that independently from each other. So you want to really verify them independently also for the worst case execution time. So these are really the objective and interest for a project to go into that robust partitioning use case. How do you do that? Still, the traditional time and space partitioning capabilities that you can find in DO-OS and were used for integrating modular avionics can still be used there. That's a really good candidate. Because we're talking about independency, about partitioning, you should not forget the error containment. Because it's good to think about the normal case of the behavior of your system, but sometimes, in particular, if you embed a DAL-E application that you don't exactly know where it's coming from, there are some chances that it could fail. And then if you don't provide the proper error containment, the management of this error could interfere as well with the rest. So the error containment is also something that needs to be kept in mind in such solution. So with this, what we want to do, pretty much control the shared resources. As pointed out by Guillaume, these are usually the focal point we will look at in order to see what are the interferences and how we can mitigate them. So that's what we'll look for, the shared resources. And the way to control this could be by design. So that's one of the approach that can be addressed. So either you can monitor what's going on to control the behavior and ask the OS to do that, or you can apply a configuration that makes it limiting interferences by design. So these are two ways to do things, and pretty much you ask the OS to set up that configuration at initialization time and don't do anything later. So what are the caveats of this solution? So usually when you want to do really a full robust partitioning, in particular to go up to incremental certification, that's going to be costly. So you may want to limit the shared resources. And that's a general trend that already applied when you were in single core and doing the same thing, is you may want to limit shared resources from that point of view. So which means that you will reduce the capability of the platform to achieve that. And also when you will mitigate the partitioning, mitigate interference using partitioning, you may have a performance impact. In particular, one of the examples I may use later on, you have a risk on some particular multicore processor, but they were old generation, that in the end, if you restrict too much or use time partitioning, for example, to serialize the access, in the end, you have the same performance than the single core. So why bother using multicore? So something to keep in mind is some of the decisions you will take can have an impact also on performances. So let's look at the second case. Pretty much the second case, which are all the other multicore platforms, this is a subset of the first one. It's just that you may not mitigate all the interferences. So as part of the verification that Guillaume will talk later on this webinar, pretty much you can still mitigate the one, and for the interferences that are mitigated, maybe you don't need to test with the whole system in place. So that's an option indicated by CAST-32A. But for the one that have not been mitigated, you will need to set up the framework for evaluating worst case execution time with everything in place. And the obvious caveats about that is, let's say you make a change on one of the applications, then that means that you may have to redo that test again with all the application in place. So that can be quite a huge importance on your project when you do update. So that's something to bear in mind with this approach. So usually that's where you want to apply some same mitigation that you go in case one, but maybe not all of it, because you don't want to do integrated modular avionics, you don't want to do incremental certification, so you may not need to go as far as you would do for case one. So for the following part, I would say, of my presentation, I'm going to pick up some use cases, example of how we can partition resources. But something to bear in mind is this is a multi-dimension consideration. We want to look at the shared resources. When you look from the hardware point of view, most of the shared resources or most of the resources of the hardware are managed on a per core basis. While you may want to look at it from the application point of view. And you may have multiple applications on one core or an application using multiple cores. So you can see that you have a multi-dimension approach on how you are going to articulate this analysis and identification and mitigation of interferences. So something to keep in mind. So one important thing is the shared resources also come from the way you do your software design and the core allocation, meaning where do you allocate the application? For example, do you allocate all the application that will use the Ethernet on one core? You spread them around the multi-core. So the way you will do allocation and your software design will have a direct impact on what will be pretty much the interferences that you can face. And that's something you need to keep in mind, that your design may need to be updated to simplify also the partitioning. So one aspect to consider is this allocation. So some example. So for example, in particular, if some of you have read the Multicore report that you can find on the EASA website, you can see that there's some example of scheduling on the multicore. One of them is to say, let's serialize the access to the resources. And which means that you have only one application that runs at a time, whether it uses all the core or not, only one run at a time. That's a way to serialize the access to the shared resources. But with this approach, is the performance of your system going to be as expected? Or do you need to switch to the second use case where you run in parallel? Because in particular, when the application or not multi-core application, there's still a lot of single core application around. So if you use the previous use case, that means that you're wasting some computing power from the other cores because only one will be used. So here, when you start to use in parallel, we can see that obviously application 1 and 3 at the beginning of our schedule are going to interfere with each other, in particular with the access of the memory or the cache, and on the I/O if they're doing some I/Os. So here, this is the kind of schedule and approach that really will trigger interferences that we'll have to analyze. Still, some aspect is you can use the time partitioning approach to maybe try to align the access of the resources not at the same time. For example, if you have application 1 and 4 that use the Ethernet, let's not schedule them at the same time. So that way that may remove a shared resource from the scheduling point of view, so by design. So also here, one capability you can find in the OS is some synchronization point between the schedule. So that way you can really make sure that your scheduling is aligned between them to allow that removal of executing in parallel the access on some shared resources. So that's one example of one mean to do some partitioning. So let's look at the resource control right now. You talk about the scheduling, so now the resource goes to the other objective of CAST-32A that Guilhem highlighted in the introduction, which is to identify the resources and see how we can mitigate them. Let's start with a simple one. So the simple one is pretty much one where you directly map the real-time clock, in my example here, to each of the guest operating systems to be used. So here we rely pretty much on the hardware to control the partitioning and the concurrent access to your real-time clock. So to comply with the CAST-32, you need to verify that there's no side effect of doing this. So here, usually you need to have the full hardware documentation, which is one of the aspects you may not have. So here, that use case, if you don't have all the documentation available to show that it's safe to do that, or at least you can get information on the interferences, if you don't have that information, that may be risky to take such approach. But that's a possible approach, which is pretty much easy to do. And from the OS, in particular from the hypervisor point of view, you just ask the hypervisor to open the access and leave it to the hardware to manage this. Still, you need to evaluate whether there are interferences because in particular, if they are mapped, the real-time clock is mapped at the same address for both guests, there are good chances that your interconnect will serialize the access to it, not allow it at the same time. If it's serializing, if it occurs at the same time, that means that one will have to wait while the other one is making the access. Maybe that's not significant at all, but you need to verify that to be sure. And also, not all hardware resources will allow this. In particular, some will have some, I would say, vulnerabilities, like that will prevent you from having guest 1, which would be a DAL-B application. We also have DAL-B application, and guest 2 that will host a DAL-E. If there's no protection in the hardware, then you will not be able to do that because you will break the partitioning that you were relying to do mixed criticality. So just be careful of that. But that's a simple approach. There's some mitigation that could apply because the hypervisor can control not only opening the access to it, but it can also control which mode is allowed. So in particular, it can do it in read-only. So in particular, when one guest just wants to read the clock, that could be safe to put it in read-only and allow concurrent access without further control of the hypervisor. The other approach that can occur at the same level of safety would be to push to the guest OS the mitigation and to synchronize the cooperation, and cooperate to write into such device. So that's one example that can be done, which is very simple from the OS point of view. Another one is a client server. So usually it's where, for sure, you cannot allow all the guests to access at the same time the shared resource because you will have side effects, the interference will be difficult to handle. So in order to simplify this, you are going to allow only one guest to access, for example, here, the Ethernet. So the typo on the slide should be Ethernet all the way and not translate to CAN, but just a typo. That's an example. It could be any kind of device. And that guest is going to act as a server. So it could be an I/O server. That's one model that you can apply in your design to do that. And that server is going to wait for requests on a safe IPC, for example, from all the other clients. So which means that you still have a shared resource, obviously, which is the memory and the cache is over there. But as we mentioned at the beginning, that one will occur anyway. So here we have removed from the equation the concurrent access to the Ethernet to only move it to the servers. So that's another approach. The caveat of this approach means that the client will have to wait for the server to process his request. So this solution will introduce latencies. So you need to verify that it's acceptable from your performance point of view. Still, with this, you can define priorities, or you can define, for example, allow one guest to be treated in priority compared to the other one based on your use case. So that's your use case that we define how you do that. Another way to do this, in particular, if you have guest OSs that you want to be unmodified, meaning you don't want to touch it, and that guest OS was thinking to address directly the Ethernet, you can virtualize, which means that you can put the driver inside the hypervisor instead of the server guest. So the hypervisor will trigger or will detect that request and translate and act as a server to go to the real device. So that's another approach that could be maybe more efficient because the hypervisor reacts immediately on the request of a guest. Still, the hypervisor will serialize the access when multiple guests will use it. Here again, you can define priorities to see which guests you want to address in priority. So that's another kind of partitioning access you can apply. So we talk about cache memory, and that's the one that you cannot avoid pretty much. It's really difficult to partition. So it's more complex to control. So one way to do that, you have some multiple processors that have multiple memory controllers. So you can, for example, allocate application on cluster of cores where you can have a dedicated core, memory controller to access it. So that's a way to partition it. So that way you can use a different path in the multi-core implementation to access that and reduce the interference or remove it. Still, that's where the documentation of the multi-core is going to be important to see how far you can do and if you can really remove the interference or just reduce it. But even if you reduce it, that's a good start. So that's about the memory controller. Otherwise, memory controller will be really a shared resource that you will have to evaluate the level of interference. The other one is the cache. So the cache on the core, that's fine because it's dedicated to a core. Again, that we are back to the original Unicore approach in which if you have multiple applications on one core, you deal with it, but that's not the point of the discussion today. So here we'll more talk about the shared cache because all the core can access it pretty much at the same time and ask for a reload of the cache with some data where the other one was not expecting this, so that cache miss and reload of the cache can introduce interferences. There are several mitigations for that. First of all, depending on your application, you can just deactivate that cache because if the application goes back and forth in the code and data, maybe it didn't bring any benefit for that. So one way is to disable it. If you still need it, one way to partition it is to allocate the whole cache to only one application or to only one core. In that case, you still have the benefit for the cache, but not for all applications, just for one. That's a partitioning capability. The other one is, depending also on the cache structure, you can partition inside the cache, which means assigning some line to some cores and some other line to the other cores. It reduces the benefit of the cache, but still, you implement some partitioning in there, in alignment with the documentation of the multi-core processor to see if there's no other side effect of doing this. But that's another approach. So that's usually some ideas on what you can do regarding the partitioning on example resources. So to summarize what we talk about, and I see some chat and Q&A going on, please continue to put some question in there because I only covered some example of solution to do some partitioning. So please go ahead and put some question there. So to summarize what we talk about, so for case one, robust partitioning, typically when you want to do AMA, the assumption is that all interferences have been mitigated, and the RTOS is a key player here to put this in place and enforce it, because usually that's what you request to the device. It's going to enforce the configuration that makes sense for your use case. It's not artificial intelligence, it's not going to decide by itself, but it's enforcing the best solution for your use case. And still, at that point in time, when we have put the design in place, mitigation has to be verified, and that's what Guillaume is going to talk about. Same thing for case 2. Case 2 is a subset of case 1, meaning we didn't mitigate all the interferences, but some of them, hopefully a large amount of them, have been mitigated, but still they will need to be verified. So for any case that you will use when you will design your Multicore platform, you will need some verification. And in all these solutions, having flexibility on the OS is a key point that we wanted to put in our solutions to allow that trade-off between performance of the system and formal safety certification, because there's not one solution that fits all. You need to review your hardware, you need to put in perspective of your use case and select what are the partition solutions that will make sense to mitigate the interferences. And at that point in time, when you reach something that you are confident that doing a good job, you still need to verify it. I will hand it over to Guillaume. It will talk to you how you can move to that verification aspect.
Thank you. Thank you, Oliver. So I'm going to start my presentation, and I will add some comments and refinements of the points that Oliver is making. Thank you very much. So one of the take-home messages is that, it's a very, very good news for us, is that independently of case 1 or case 2, there is still the activity of verifying that the mechanism that you put in place is correct. Olivier and I did a presentation at the conference, at the SAE conference, about a year ago or 2 years ago, and it was to specifically address the question of, so why do I need to do the verification myself if the third pack of the real-time operating system provides everything that I need? The answer is, no, hold on a second. The operating system provides you the mechanism and the flexibility that the end customer can use to fit your individual requirements and the peculiarities of your application. Whatever mechanism you do, it is then your responsibility, it is where we want to help, to provide the evidence, particularly to certification authorities, and the higher the criticality, the deeper the analysis needs to be performed to show that this mechanism is effective. So in one sense, the robust partition case 1 and case 2 produce, in my point of view, a similar amount of work, because the work is different. First one is to say, well, I don't need to do a detailed analysis because I have a robust partitioning mechanism. What is your evidence that your robust partitioning mechanism is effective? The other one says, I don't have a robust partitioning mechanism, therefore I need to provide the evidence of what is the actual interference that my application performs. So in both aspects, you have to perform a level of verification. And it goes back to one of the principles that where we start, and people who've seen my presentations before, one of the principles says, you shall trust no one. Meaning, if there is a fundamental piece on your hardware, software, computer architecture, which is fundamental for your argument to comply with worst-case execution time analysis, let's say partitioning, cache, isolation of the cache, this mechanism needs to be verified, and therefore you cannot trust it. For example, another aspect here is that the level of detail at which you need to be looking at the interference still is not clearly defined. For example, going back to what Oliver said on his previous slides, let's go back for a second and we'll at the comment here. And is that if you provide cache partitioning, therefore, I guarantee that there is no interference. Except that we've seen in some of the systems that even the mechanisms on chip that provide cache partitioning support has some hidden channels of interference. Because the internal, the microarchitectural implementation of the cache does have some shared resources. One is called the meter status code register, which is that still in the cache, if it is partitioning on the output channel, you still share a single exit to the cache. When the cache is partitioned, yes, you may prevent one task or one application evicting lines from the other, but where there's a cache eviction, you need to go to memory, you're still competing on a single channel out of the cache. So this is just to illustrate that for every level of assumption of partition mechanism, there is a thought process that needs to be verified. So, how we have understand that operating systems provide you partitioning, flexible mechanisms to configure dependent application. Our job then comes in and says, show me what is the evidence to show that this partitioning mechanism works. We have it, we developed a methodology that uses a combination of a sub-engineering process to understand what are the questions you need to ask and what is the evidence. And the main principle is to use the concept of interference generators. We call it Rapita for generating demonic adversaries, maximum interference. Now, we have developed a collection of Rapita that are small applications extremely carefully designed and developed to generate stress on a particular shared resource. The idea is that if you run an application, let's say running on one core, and you run then these interference generators, by maximally generating competition on that resource, you can quantify what is the maximum interference that this application can suffer. If there is a partitioning mechanism that is effective, the interference will be bounded, and therefore you're okay. That's your proof. If the interference is not mitigated, then you're able to quantify it. So I'm going to go through that methodology in more detail. How do you quantify it? We developed a standard mechanism or process to perform the static analysis. Now, a couple of questions that people keep asking says, but the only thing I want is a tool that I press a button and I get a worst case execution time. So I'm sorry this doesn't exist. Because even if you had a perfect tool that is a potentially non-computable problem, you wouldn't still like the number. So the process of worst case execution time analysis is much more delicate than that. It starts by having an understanding of what are the requirements, what are the questions that you need to understand. For example, let's say that we have as part of the analysis of what are the topics, the questions, the evidence we need to generate is that we have a system provide robust time partitioning, or what is the cache configuration and what is the effectiveness of that cache partitioning. So understanding the questions that for which you need to provide answers delimit the scope. Early analysis stages could be, the questions can be, what is a adequate configuration for the characteristics of my system, or even which processor do I need to use. For later stages in the development process is more, what is the certification evidence I need to produce to guarantee that my partitioning is effective. Once you have the understanding of the requirements and what are the questions, there is a part of the analysis which is the understanding phase, which is what we call hardware characterization. So what are the elements of the hardware architecture, not only of the CPU, but also the system on chip, the other devices you may have on the system, including custom FPGAs, and as well the software architecture, including, for example, the ability of a hypervisor and what are the impact of this hypervisor. So in particular, for example, if you have a level 2 cache with the ability of providing partitioning, how do you verify that capability exists and how this relates to the architecture of the system. So the requirements and therefore the questions you need to do worst case execution time analysis for, and then the understanding of the hardware leads to the next step, which is you want to define a set of experiments in the same way you do a test design with test cases and test procedures to provide evidence of the correct behavior, the expected behavior of that particular feature, or the quantification of interference. And this is where, following the same principles of DO-178, you will have a decomposition, let's say, from high-level requirements, low-level requirements, tests with the right traceability that allows them to, at the end of the process, be able to track back the reason that the analysis and your tests are complete, and that you can trust the results of those tests. Now, these test design, which is basically experiment now, converts into an implementation of the test. And this is where the automation can facilitate and provide a clean return of investment argument. So the experiment here would be, I have an application run on core 0. I have implemented a partitioning mechanism. The experiment I will do is I will run that application on core 0 against very well-crafted configurations of rapid image that will generate interference on a potential set of resources, and there can be multiple configurations of these sets of interference. The definition of the test, we developed it in for example, an Excel spreadsheet that allows an automation tool to run those tests and generate the evidence. So the process of the running of the tests and the collection of the evidence is the part of the process that can be automated. You then need to have still, and the part of that process of those tool chain is as follows. The input to the tool chain is a collection of tests. The traceability of those tests and why these tests are correct, reviewed, and complete, this is part of the intellectual process that needs to be put in place anyway. Once you have those tests, the run of those tests, we use our tool Rapita, that together with a platform support package, which is a minimal level of support on the hardware to be able to provide the hooks into which to inject the rapid image and a collection of rapid images. Those provide an execution of those tests on the target that gets analyzed by a tool called Rapitask and Rapitask. Rapitask provides a scheduler visualization to understand, to visualize that indeed the right time slots, in the same way that the diagram that Oliver was showing, that which application runs on which core, and then, for example, that when application 4 run starts, application 1 has finished. And at the end of the analysis process, when you have a collection of results. And the result is what then gets reviewed and answer more questions. So the setup of the process requires some integration activities, which is what we call a platform support package, plus the configuration and porting of these rapid events, and the way making sure that the tests integrate on the tools integrate on the target. Once that integration is done, then the whole process can be repeated and automated, which means a change, a new test, change of configuration can imply a whole re-execution with minimal effort. And once the results are produced, then you have an intellectual process to understand the results. These results most likely will generate more questions, which require a reiteration, or at the end, when the evidence is enough, the question is still open of what is enough. When have you done enough? Then you generate information to complete for the software complement summary. So linking back then the process to what we said about CAST-32A, the requirements phase really covers the MCP planning 1 and 2 and the resource usage 1 and 2 stage, which is understanding what are the challenges you need to perform. The test design is really what we call resource usage 3, which is the hardware characterization. What is the interference? And the MCP software 1, which is the final worst case execution time, and the characterization of the interference channels is part of the final stage, which is software complement summary. At this stage, I would say that we envision that you would have to do that iteration twice. One is to perform the hardware characterization, in which what you run is, let's say, a well understood crafted piece of code, like a rapid image itself, against others, And that, because you understand exactly what is the resource usage pattern of that particular piece of code, you then can understand how that particular access pattern gets impacted when it runs against other processes. This is part of the hardware characterization. The second iteration is when, going back to to be able to perform the generation of evidence of applications independently, is when you run one application alone, the minimal harness in which you can run, and then that application gets executed in isolation and against a whole collection of configurations of rapid events to identify the maximum interference. You can then understand which experiments you need to run, because the previous phase tells you which are the resources which are susceptible for interference. So, a quick note of that: we'll make the slides available and the video available for later users. But one of the key points to address here is that the satisfaction of the objectives requires input or activities from three players. One sense is there are some activities that only the end customer can perform because they own, for example, the PSAC or the PHAC. There are activities that would require input and support from the RTOS providers and the hardware providers. Key to the multi-core timing analysis is the understanding of detailed information on how the CPU works and the internal or the configuration of the RTOS. So the support of the general access information, which we expect to be available as part of the third pack, needs to be provided by the RTOS. What we provide as solution together with tools is to perform activities that feed into some of these objectives. Key one is, number one, is to provide the hardware characterization up to the level what is deemed necessary, and the worst-case equipment analysis of the application. And this requires as well support from both the operating systems and the customers. So, just to visualize and demonstrate how the approach and the process works, we prepared a demonstration of how the process is able to analyze an application on a T2080 processor. And because of the short time that we have available in the session, we've just done a pre-generated video, but my colleague Christos is available for questions later on. We know that there are some web browsers that are not able to display video. If you don't see the video, don't go away. We have recorded the session, and the session will be available later on. As soon as the video finishes, which will take about 10 minutes, then we'll go back to the session of questions and answers. So just spare me a second while we switch to video.
Hello, my name is Christos Rapita, and I will be presenting a demo of our multi-core timing analysis approach. This demonstration shows our testing methodology for analyzing the effects of interference on a T2080, which runs a partitioned configuration of VxWorks. The T2080 is one of the more commonly used processors in the aerospace domain. It has 4 cores, 2 megabytes of shared cache, a DDR3 memory controller. For this demonstrator, I will be focusing on the effects of interference originating from the DDR. In the first step of our methodology, the objective is to understand the performance and the characteristics of the hardware itself. For this, we need to execute the rapid daemons in isolation in their own core, with the rest of the cores running in idle. For the purpose of this demonstrator, we've selected a DDR3 rapid daemon to execute on the first core of the system, while the other cores are set to be idle. Here we see a rapid time report of the scenario where we've executed a rapid daemon which stresses the DDR on core 0, while the rest of the cores in the system were set in idle. From this report, we can see that the rapid daemon took each invocation of the rapid daemon took 14.2 milliseconds in minimum, 14.4 in average, and the maximum observed time was 14.7 over about 1,000 iterations. From the plots in the rapid time report, we can see that the rapid daemon is when it's executing in isolation is rather predictable, since we've observed about a 0.5 variation in its execution times. The second step of our methodology is concerned with understanding the sensitivity of different operations in the hardware when there is interference in the system. For this, we execute the same rapid daemon on core 0, which is being instrumented again by rapid time, whereas the rest of the cores in the system are executing copies of the same rapid daemon, all using the DDR. Here we see the report that was generated from executing the same rapid daemon on all the cores. Just from this report alone, we can look that there is quite a bit of variation in the execution times observed. With rapid time, we can also view a direct comparison of the two scenarios. The observed execution times when running the rapid daemon against copies of itself is an increase on average of 33% in execution time and 81% overall. What is more interesting is the distribution of execution times of the rapid daemon. This plot shows a histogram of the execution times that were observed in the two scenarios. In green, we have the execution time distribution of the rapid daemon when it executes in isolation, and in red we have it with interference. It is very clear that we have a significant increase in execution time in this case, not only nominally but also the distribution of these execution times is a lot more significant. What this information is hinting us is that in applications that are very reliant on accessing the DDR, we can expect an increase in variability in execution time in this platform. The first two steps of our methodology will need to be repeated for all the identified interference channels in the system. For the purpose of this demonstrator, we will just be restricting the scope to the DDR, and we can now move on to the next step of our methodology. The next step of our methodology is to run the application baseline. The purpose of this is to analyze the behavior of the application when it executes in isolation. This is where we get a feel for potential problem areas, and we also can do an assessment on the quality of our test data. The application that we will be analyzing as part of this demo is configured to run within a VxWorks 653 partition with its core affinity set to the first core in the system. The application itself follows the canny edge detection algorithm, which is a rather popular image processing algorithm. Here we have a rapid time report of the application executing in isolation on core 0. Where I'd like to start is the invocations tab. In this tab we have the invocation timeline, which is a timeline of the execution times of the root function. From a quick view at the data, we can expect that the software itself is actually rather predictable. In the execution time tab, we can see some statistics of the execution times of the different functions in the system that have been instrumented. These statistics include minimum, average, high watermark, which is the longest execution of the root, and the maximum execution time. And for all of these metrics, we can have the self-execution time, which is the time spent in the function itself, excluding any sub-functions that it may have called, and overall is the overall, which includes that execution time. In the contribution time tab, we can see the proportion of execution time contributed by the different functions in the system. And what I mean by this is that we take into account not only the execution time, but also the number of invocations of each function. So a function with a relatively short execution time that was invoked many times, it would have a greater contribution as opposed to when it executed less frequently. In the last step of our testing methodology, we will analyze the application sensitivity when it is executed with interference. Again, for this demonstration, we'll be focusing on interference originating due to accesses to the DDR. Here, the configuration that we have is, again, the application under analysis is statically mapped onto core 0, whereas the rapid daemons are set to be executed on the rest of the cores in the system, creating traffic on the DDR. Here we see a comparison of the two runs of the application, one which is with the rapid daemons generating interference on the DDR controller, the other one without. Here we see a rather small increase in execution time in the order of 1.3%. What is worth noting, however, is the increase in variability. So in many systems, even though the execution time itself may not increase on average significantly, we typically see a substantial increase in the range of values we observe. Here we have the execution time profile of the two different runs. Again, the application itself is rather predictable. However, if we zoom in to take a much closer view on what's happening here, we can see that in the scenario where the application was executed in isolation is quite a bit more predictable. However, when we added the interference, we observed a further spread of the execution times.
One comment I want to make about the results is that even I myself was surprised that on a application that generates key interference, you have up to about 80% increase in execution, but the real application that actually uses a lot of memory, on that particular interference channel, the interference is very small. It is what it is. In that case, the partitioning mechanism was effective. The only way to say whether that is effective or not is to run those experiments and generate that data. There is somebody that says you will speak of stress tests. Is it sufficient to test for worst-case execution time, or do you need to prove it mathematically? What is the approach to prove this? So how much time do we have? This is the kind of thing that may take a very long time. Brief answer to that question is the analytical computation of worst-case execution time through static analysis is, in most cases, not feasible, especially if there are data dependencies in the application. So what I would say is that only in the certain very restricted conditions, an analytical approach is feasible, which means that the only approach is based on defining worst-case scenarios that generate the stress cases. However, the difference between a single core and multi-core is that which are the worst-case tests that generate the longest execution under any sort of interference is much more complex. Another very good question from the same anonymous author says, if your tools are used, two qualifications has to be performed, right? And the answer is yes. There are some customers that have, our tools are 2QL5, or we have DO-178 qualification kits up to DAL A, so that's, and they've already gone through a certification. So the tool itself is okay. There is an argument, and some customers use that they do not need to qualify the tools because there's some manual review process that verifies that the output is correct. But both options are available. I think it is much more cost effective to use tool qualification keys rather than to review manually. But yes, some of the tools need to be qualified. We are now leaning, and we have these very long discussions, whether the rapid demons themselves need to be qualified. Rapid demons are not a tool, are a piece of software. Therefore, the DO-173 doesn't really apply. However, there is to be a level of evidence to demonstrate that the tool, the rapid demons, have been designed properly and they generate the right behavior. So we call that approach that the rapid demons are qualifiable. It doesn't mean that the qualification evidence is really a qualification kit. It's only part of evidence. Right? Oliver, that's a question for you. Christoph says, what is the hardware dependency to support the cache partitioning?
So that's a good point. That's something that needs to be looked at. So usually the processor documentation gives you some clues about it, which means that you need to have the possibility to configure the cache to associate some lines to a core. So usually a dimension is usually the core. So then that's where the multi-dimension aspect comes into play is if you have one application per core, that's fine. Then you can apply a configuration at startup time that allocate that line to a core, and implicitly it will be allocated to the application. If you have multiple applications, then that starts to be a little bit more complex, and the OS can help there, because when you will switch from application, that's where you can change the configuration of the cache at that time. That will add a little bit of more overhead, but that's possible. So, but the first step is really to check what the documentation of the processor is allowing to do. That's the first step, usually.
And of course, assuming that the processor provides support for partitioning, which is always the case.
That all of them does.
So the first two questions were for Christoph. Sorry, these questions are from Jason. So there's another one for you. He says, we have quite a big question, so we want to go through here quite quickly. How many certification programs are actively using the partitioning methodology approach you are discussing? Oliver, that's you. You're on mute.
Yeah, sorry about that. So could you rephrase the sentence, because I thought you were.
Yes, sorry. He said, how many certification programs are actively using the partitioning methodology approach you are discussing?
So I would say that all the programs that use Multicore have to use it. So the partitioning methodology, in fact, there's not one. There are more partitioning capabilities that you can use. And each project or each program will use something different from that point of view. There's not one solution that fits all. Usually, that's why you need to do analysis on that. But I would say that all projects that use Multicore, they have to do some sort of partitioning. Otherwise, answering CAST-32A is awfully complex.
And this leads to the next question, which says, are certification authorities requesting this level of partitioning verification occur? If so, are they requiring this for all DAO?
So, in fact, I would say they don't request this. It's up to you to do the partitioning, I would say. Usually, the partitioning is here to help to simplify the approach. But as soon as you use partitioning, most of the time you have a performance impact. So it's your choice. So usually the authority are not going to impose this to you. It's more you to select that you want to do partitioning and which partitioning capabilities you want to use that fit your use case, still not reducing too much the performances. So I would say no, it's not required unless you want to do mixed criticality. So let's go back to the DO-178C objective that partitioning needs to be established, which is required when you want to do mixed criticality. So that's where we are, I would say, at the middle of two things, is mixed criticality and reducing the effort for the CAST-32A.
Yeah. The other part is, are they requiring this for all DAO? Well, no. What is required different for DAO is the rigor under which you need to do the interference channel analysis. CAST-32A doesn't require as an objective partitioning. And I say, Oliver, it makes life easier. There is one extreme of partitioning, which is you don't use multiple cores. So you partition the resources by only allowing one application to move one core at a time. Therefore, we simplify all the way to a single core. But then the processing penalty, you're basically using the multi-core at a much lower capability. But if it still fits, then you don't have to do CAST-32A. What we've seen before is customer decide to do that. Customer goes, each customer comes back and says, oh, we have a new functionality that I need to add. Or very sorry, it doesn't fit. Oh, but you have 4 cores and you're only using 1. Can you put it in the other 3? So eventually, one way or the other, it will come. A final question from Jason. Can you raise a TQL required for the Rapita tool when using the scenario you're covering? We believe that is TQL 5 because it's used as a verification tool. The Rapid daemons, as I said, they are not tools. They are pieces of software to support the testing process. And more than thinking of a tool qualification level, is more that there is a qualification activity as if it was part of your system. They don't have an impact on the functional behavior, but have an impact on the performance behavior. So they need to be verified as any other piece of software. So that's a question from Jason. We have another question from Martin. He says, I assume there are preferred multi-core processors that have a compatible or good architecture for safety-critical systems. Can you name some examples from your experience? That's a very tricky one. It's basically saying there are lots of cars in the market. What is the best car? So it depends on what you need. If you like a flashy car, that would be a Ferrari or a Bentley, or it could be a Ford Fiesta, or it could be a bicycle, because you don't like cars. This is what we actually propose at this level, and maybe you have some other questions, Olivier, is that there is a whole range of processors and systems on chip available in the market because there are different needs. And one of the initial activities is the hardware selection and the selection of the critical configuration settings that maximizes the performance and the predictability, if you want, analyzability of that processor. This is not a trivial task, and it can take some time to perform. You have anything else to say on these, Oliver?
No, I think you perfectly said really what the challenge is.
Thank you. Another one for you from Gotham. It says, VxWorks 653 has options to configure for time and space partitioning in XML files by the user. Is it also possible for resource partitioning to be done in a similar way?
Yeah, and in fact, that's what's done in the Multicore edition of 653, and the new name of X653, which is the Ellipse virtualization platform, that's where you find in XML some entries to enter the resources, and then you can allocate them to the different VMs. So that's how you can partition them.
Okay. I have a comment to make at this level. Of course, you can only configure the resources for which it is possible to configure because there's hardware support for that. There are some, when you look at a T2080, there are some resources that there are no performance monitoring counters or any mechanism to physically enforce a partitioning. And these free resources, if you want, there are still the ones that need to be analyzed as if there was no partitioning at all. The ones that you want to partition, you also still need to have the mechanism to verify that the partition is effective. So we're always going want to do one or the other. So the question from John says, please confirm what I thought I heard you say for resource control. To mitigate use of resources via partitioning, priorities can be assigned to individual partitions. Can this introduce a starvation for resources?
So yeah, you have a risk, because if you keep a resource being shared, even if you assign priority, then the traditional side effect of sharing priority still apply. So starvation is a risk. Typically, if you assign a low priority for a low criticality application, then maybe you can starve and will never access it. So I would say that the traditional approach about this really apply. So that's why this approach may be less interesting to do, but that's still one option. And depending on the use case, you may need to use it or not.
And again, the issue is the configuration of these priorities of partitioning or control allocation can have side effects by delaying everything. So in one sense, you always need to provide the implementation and the verification of the activity, which relates to the next question. We're almost finished now. Is how is the robust partitioning different from the normal time and space partitioning we do on single core processors? So let me put some slant on this one, and then you can finish it off, Oliver, if I may. So space partitioning really is memory protection. So that's sorted. Let's go to the side. The time partition on single core really means that you execute applications one after the other. The only thing you are partitioning is giving a slot to an application, actually filling that slot. Multicore is more complex than that, because the dimensions of the number of things you need to partition is not only time. You may give us a lot of an application, but the application uses access to the coronet and uses some cache or uses some of the shared resources. So the partitioning on the time partitioning is much more sophisticated, and that's why the definition is very well crafted of robust resource partitioning. And time can be one of the partitions, or one of the resources you are doing, but there is more than that. Enforcing time partitioning on single core is very easy. You start the process, when a timer expires, you stop. Enforcing resource partitioning, that's much more difficult, because you have guarantee that you count the right access of resources to the right application. And one of the things that we observe is that there are some CPU architectures where the performance monitoring counters do not count the right things and do not count the things right. So even there is a fundamental process assumption that you need to provide evidence that your measuring device is correct. Then you can build on top of that. Remember, there are some of the resources for which you cannot control because you cannot count them. Hardware doesn't provide support for that. Anything you want to say on that, Oliver?
Well, I think you said most of it. We just word it a little bit differently. When you were using time partitioning on single core, at one time you partition all resources because you have only one core. And usually the partitioning, the mitigation aspect you have to take care of, were usually occurring at the moment where you were switching from one application to the other one, which means you stop one application, and before you start the other one, you do some mitigation like cache flush, like flushing buses data and things like that. And with multicore, because of the parallel execution, that mitigation needs to occur all the time. So it means you need to review completely the approach to take this into account. You don't have that simplification that occurs. And this is why the example of running one application at a time on all cores is a way to recreate what we did in Unicore to apply for simplification, but it has an impact on the system performance.
And on that note as well, there are even interferences which are not related to CPU calculations. So you could have a stream of network traffic that collapses the coordinates, but you have no control because on the end of the Ethernet, you may have a babbling idiot that is generating vast amount of trace data. If there is no ways to close or limit that traffic, that can provide an unbounded amount of interference or a large amount of interference. So the time partitioning, the space partitioning is one aspect. The time partitioning and the resource partitioning has all the dimensions of multi-cores. We have one final question. We are running a bit late, but thank you for your patience. How does time partitioning scheduling affect the timing considerations? Well, greatly. And the problem is that the definition of which is an optimal scheduling policy is extremely difficult because, again, the two applications that are running parallel on different cores may have different sources of interference and different impact on interference. The single core, so the optimal scheduling where only timing is an aspect, is still an open research problem. The multidimensional aspects of the time depends on which resources are shared, which then affects the timing, which then affects the scheduling, is, as far as I know, still an open problem. There are a lot of simplifying assumptions that you can make while not trying to do an optimal schedule. But yes, the answer is yes. Putting obviously two applications running simultaneously in parallel that are affected and they collide into the same resource may have a big interference. Providing applications that use heavily resources but they are independent may not have an impact at all. In any case, that scheduling needs to be verified.